fluid comes to the surface as an emulsion of oil, water, gas, and solids. Emulsions in the oil and gas industry are either classified as water in oil or oil in water, depending on the ratio of the volumes of liquids. Gas brought to the surface is usually wet gas, composed of dry natural gas like methane, mixed with liquid natural gases like ethane and butane. All of these components are separated using multiple principles of separation to achieve the desired end products that are considered valuable. In this video, we'll explain 6 separation principles used for emulsion in the oil and gas industry. The first principle we'll discuss is heat. When separating liquids from each other, heating to certain temperatures enhances separation. When the temperature of an oil and water emulsion is increased, the viscosity of oil is decreased. This lower viscosity allows the gas and water molecules to be more easily released. Heating oil emulsions also increases density between oil and water. A heater treater is an example of a vessel which uses the principle of temperature change to aid in separation. For more on how a heater treater works, check out our Training Level 1 series. Our second principle is gravity separation. The elements in the well stream, such as oil and water, have different gravities. The density differences allow water to separate by gravity. With enough time in a non-turbulent state, the differing specific gravities will naturally separate. To picture this, think of the emulsion as Italian salad dressing. If you let the dressing set, the ingredients will separate according to their different specific gravities. The olive oil will float on top because it is lighter than the vinegar, and the solids and other ingredients will fall to the bottom because they are the heaviest. The next principle directly relates to gravity separation and is called retention time. Retention time is the amount of time the fluid stays in a steady or non-agitated state inside a separator. Longer retention time means more separation. A larger diameter or taller vessel will increase the retention time and allow more water to settle out by gravity. In this visual of a sample of emulsion from a free water knockout, you can see 3 layers: oil, water, and solid, which separated over time. Our fourth principle of separation is agitation. A production fluid is agitated when it hits the diverter plate at the inlet of a vessel. The sudden impact on the plate causes a rapid change in direction and velocity, which helps break the surface tension of the liquids and start the separation process. There are many styles of diverter plates and separators, and the choice will be made by the attributes and volume of the well stream. Coalescing is related to the agitation process. During coalescence, water droplets come together to form larger drops. In vane-type mist eliminators, droplets are removed from the vapor stream through inertial impaction. The wet gas is forced to change direction, causing mist droplets to strike the vanes and coalesce with other droplets, eventually falling. This inertial impaction also occurs in mesh-type mist eliminators. Gas must flow around each strand of mesh, and when mist droplets strike the filaments, they adhere and coalesce to form droplets large enough to fall. Submicron droplets are forced to zigzag through the close-packed fibers with Brownian motion and will eventually strike, adhere, coalesce, and drain. Our final principle of separation is the use of chemical demulsification. The chemicals move to the oil and water interface, weakening the surface tension and enhancing coalescence. Knowing which chemicals to use and the correct dosage can be complex, but the desired effect will minimize the amount of heat or retention time required for separation. Still have questions about separation? Drop them in the comments below or contact an expert at your local Kimray store or authorized distributor.